Welcome to this video tutorial. In this video tutorials we will touch some of the things that we have learned during the different units of statistics 2. So I recommend you to pause the video and read carefully the statement, and then after that I will develop the solution. Well, the main goal of this exercise is to present you how to compute the likelihood function in order to obtain the maximum likelihood estimator of a specific function, in that case of an exponential one. If we define the function, in that case we can define with lambda or with theta. In that case we have defined it with theta. The density function is equal to theta multiplied by e power 2 minus theta multiplied by x for all the values compressed between 0 and infinite, or 0 in other case. We know that we build the likelihood function multiplying as the multiplicatory of the function, the density function, applied to each element of the sample. If we consider that we have a sample of n elements, we will apply each of the elements to the function, so we will have theta multiplied by e power 2 minus theta multiplied by x sub 1 multiplied by theta multiplied by e power 2 minus theta multiplied by x sub 2, and so on till the last element theta multiplied by e power 2 minus theta multiplied by x sub n. If we arrange this expression, we reach the final result of theta power 2n multiplied by e power 2 minus theta multiplied by the summatory of x sub a. You can do the derivation of this expression directly, but I recommend you to apply the logarithm of this function. So if we apply logs to this expression, we reach to the final result that we have the Neperian logarithm of theta power 2n plus the Neperian logarithm of e power 2 minus theta summatory of x sub y. If we arrange using or downloading the exponentials, so we have as a final result n multiplied by the natural log of theta minus theta multiplied by the summatory of x sub a multiplied by the logarithm, the natural log of e, that is equal to 1. So now with this expression we have to do the derivation with respect to parameter. So we apply to the first part of the expression, we reach to a quotient that is n divided by the parameter theta, and the logarithm of the second part of the expression is minus the summatory of x sub y. We equalize this expression to 0 in order to obtain the maximum, and we reach to the final result that the best estimator of the parameter is the inverse of the mean, the sample mean. We should have to do the second derivation in order to confirm that this is a maximum, but in this first approach to point estimator, within statistics 2, that is enough by the moment.